Hello everyone, hope you all are doing good. I am Anjana from LearnoHub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 10, Electromagnetism. We will be discussing the topic force on a current carrying conductor in magnetic field. Are you ready for the class? Let's start. Force on a current carrying conductor in a magnetic field. Consider that you have a normal wire, okay, a metallic wire you have, then you have magnetic field, a north pole and south pole of permanent magnet. Okay, here there will be a magnetic field from north to south direction, there will be field lines. Okay, for a normal bar magnet you can consider, here we have the north pole and here we have the south pole, this is your wire. Okay, now do you think there is a displacement for this wire? Does the wire move because of magnetic field? No, but when a current flows through the wire, you are connecting it to a battery, a rheostat and a key, and current is made to flow through this wire. What happens is the wire will get displaced. There will be a change in position of wire. The wire will start moving. Okay, this motion is created because of a force. So you have to remember one thing, a charge which is moving in presence of magnetic field will be experiencing a force. Okay, so we know that many charges are flowing in the opposite direction, there will be a current flow. Okay, moving charges can only create current. Okay, so a current carrying conductor which is placed in a magnetic field will experience a force, and this force is called Lorentz force. Okay, this force is called Lorentz force. And Lorentz, a scientist named Lorentz, said that a charge which is kept in a magnetic field will be experiencing a force. Okay, we can understand this with an experiment. We'll explain it in detail about this experiment. To understand about the force on a current carrying conductor which is placed in a magnetic field, this is an experimental setup. Here we are using a horseshoe magnet. This is the south pole and this is your north pole. Then you have a conducting wire AB. It is connected to battery and cell. Here we are using wire. With the wire from A, it is connected to the negative terminal of battery. The positive terminal is connected to key and the other end of the wire to B. So this is your experimental setup. Okay, it is freely suspended. The wire is freely suspended at points A and B. Okay, now we'll discuss about the experiment, how the experiment is performed. You have to see that here we have a current carrying wire. Okay, initially it will be at rest, but when current starts flowing through it, that is when you plug in the key, what happens in this direction? Here electrons are flowing in this direction from negative positive. From positive you can see the current flowing. This is the direction of current. Okay, so due to this current, the current will flow through this wire. Yes, through this conducting wire the current will flow. Here we have electricity. Okay, due to this field produced by the horseshoe magnet from north pole to south pole, a magnetic field is produced. Okay, due to the effect of this magnetic field and current flowing through the wire, there is a force created, and this force makes the wire AB deviate from its position. That is, it will start moving. Okay, it will start moving in a different direction. Okay, so this is your experiment. What are the observations? The first observation is when no current flows in the wire, no force acts on the wire and the wire does not move. You understand? Because when there is no force, when there is no current, there is no force, right? When there is current, due to the flow of electrons, there will be electric current flowing through it, through the wire, and this electric field along with the magnetic field helps the wire move. If there is no current, there is no motion or there is no force. Okay, then when current is passed in the wire, a force acts on the wire in a direction perpendicular to the direction of current and direction of magnetic field. This is a very important point, direction of force. Okay, we'll be explaining this about this. So here you can see magnetic field in this direction. So this is the direction of magnetic field from north to south. Okay, you can see the direction of current flow. This is the direction of current flow. Okay, now the direction of movement of the wire, which means the direction of motion or direction of force, will be perpendicular to both the magnetic field and also perpendicular to the direction of flow of current. This is a very important point. Okay, so this is the second observation. Third point, if the direction of current through the wire is reversed by interchanging the terminals of the battery, the direction of force is also reversed. We have said that the direction of magnetic field is represented by B, the direction of current and the direction of force will be mutually perpendicular. The direction of force will be perpendicular to both the direction of current and the direction of magnetic field. Now here, when you are changing the current, that is, we are reversing the battery. Here you have negative terminal and positive terminal. You will be making it positive and negative in this way. That is reversed. What happens? The direction of flow of current also will change. In this direction, electrons will be flowing, which means current will be flowing in the opposite direction. So this is how current will flow. Okay, current will flow in an opposite direction. Here, the direction of magnetic field is the same. Even then, the movement or the motion or the force experienced by the wire will be different. The direction in which they will be moving will be different. Okay, that is, it gets reversed. If it was moving in the positive x direction, now it will be moving in the just opposite, that is 180-degree change, minus x direction. If it was moving in y direction along the y-axis, positive y-axis, now it will become negative y-axis by changing the current. Okay, by reversing the current. So this is your third point. You have to remember one more thing. Now, for example, you are taking a very small piece of wire. Okay, and you are placing it in this way. That is, here we can see that north-south direction, the magnetic field is acting. Okay, and you are placing your wire in this way, which means the current is flowing through the wire in this direction. Which means the magnetic field and the direction of flow of current are in the same direction. In that case, you cannot experience any force. The wire will not experience any force because both of them are in the same direction. They should be perpendicular to each other. Okay, remember, this is how they should be. Current, magnetic field and force will be perpendicular to each other. Since here, current and magnetic field are along the same direction, parallel to each other, there will be no force. There is zero force. Now the fourth point, on reversing the direction of magnetic field, the direction of force is also reversed. So two steps that can be done in order to reverse the direction of force or direction of motion. First is changing the terminals of battery, reversing the current, and the second is changing the magnetic poles. Here in this way, here we can see north to south direction, the field lines are. Now if you change it to this way, north here and south here. Again what happens? The direction will change. The direction of motion or the direction of movement of the wire will change. Okay. Here again you can say that if it was in positive x direction, the movement of the wire was in positive x direction, it will become negative x direction. If it was in y direction, it will become in the negative y direction. Clear? That is just the opposite. 180-degree change will happen. Okay. So these are the observations. So you understood what Lorentz force is. Lorentz force is a force which is experienced by a current carrying conductor which is placed in a magnetic field and current flows through it. Okay. Now let's see what are the factors on which the magnitude of this Lorentz force depends. Okay. Magnitude of force acting on a current carrying wire placed in a magnetic field in the direction perpendicular to its length depend on the following three factors. There are three factors. First one is the force F is directly proportional to the current I flowing in the wire. That is, when current increases, what happens to Lorentz force? Force also increases. Increasing current, force increases. If current is decreased, force is decreased. The direction doesn't matter. Strength of current. If the strength of current is increased, force will also increase. So this is the first factor. Second factor, the force is directly proportional to the strength of magnetic field. Magnetic field is represented by capital letter B. Okay, here again the force will increase when magnetic field strength. When you use magnets of more strength, when the magnetic field strength increases, the force will also increase. If magnetic field strength decrease, force will decrease. They are directly proportional. Now the third factor is the force F is directly proportional to the length L of the wire within the magnetic field. Okay, here the third is the length of wire. When the length of wire is increased, force will increase. If length is decreased, force will decrease. Okay. Now we know the three factors on which the force depends. Force depends on current, magnetic field and the length of wire used. Force is directly proportional to current, force is directly proportional to magnetic field, force is directly proportional to the length of the conducting wire. Okay, which means you can remove this proportionality with a constant K. F is equal to KIBL. If you are taking this constant as some 1, okay, the unit. K is equal to 1. In that case, you will be getting force is equal to IBL. Okay, IBL. Important condition is current and magnetic field should be perpendicular to each other. The force that we obtain will be perpendicular to both current and magnetic field, which means there is a theta dependence. Okay, angle dependence will also be there. Clear? Unit of magnetic field. We have studied the Lorentz force F is equal to current I, magnetic field B into length of the conductor L. From this we can get B is equal to, magnetic field B is equal to force divided by current into length of the conductor. Now what is the unit of force? Unit of force is equal to Newton, right? From Isaac Newton's name we are taking this unit Newton. Then what about the unit of current? We have studied the unit of current in the previous chapter. In electricity we have studied this. Yes, the unit of current is ampere. Ampere represented by capital letter A. So remember, here you should use small letters when you represent units from the scientist's name. Okay. Next, length of wire. The unit is meter. Okay, meter is the unit. Okay, combining all this, you will be getting the unit of magnetic field. Unit of magnetic field will be equal to unit of force is Newton per ampere meter, or Newton ampere inverse meter inverse. So this is the unit of magnetic field. Okay, then we have the SI unit of magnetic field, which is Tesla, represented by capital T. It is taken from the name of scientist Nikola Tesla. Okay. Clear? There is one more unit which we'll be discussing, which is Weber per meter square, and Weber is the unit of magnetic flux. We'll be studying about magnetic flux later. So this is also a unit of magnetic field. Okay. Fleming's left hand rule to find the direction of force of a current carrying conductor. So we have studied right hand thumb rule. What was right hand thumb rule? Right hand thumb rule was used to find the direction of magnetic field in case of a current carrying conductor when you know the direction of current flowing through the conductor. Okay. Now here we'll be finding the direction of force of the current carrying conductor. For this, what you have to do is, now do with me, you have to stretch the fingers of your left hand in such a way that the thumb finger, forefinger and the middle finger are mutually perpendicular. So this is how you have to hold it. Thumb, forefinger and the middle finger are mutually perpendicular to each other. Now what you have to do is, your forefinger should point in the direction of magnetic field. Now just check this. Here you have magnetic field B. Okay. Forefinger is held in the direction of magnetic field. Okay. Then the central finger or the middle finger should be held in the direction of current. So this is how. Okay. Then your thumb, the direction in which the thumb points will be the direction in which the conductor will move, in which there is motion or in which there is force. Okay. So here the statement, now you can study, stretch the forefinger, central finger and thumb of your left hand mutually perpendicular to each other as shown in figure. If the forefinger indicates the direction of magnetic field and the central finger indicates the direction of current, then the thumb will indicate the direction of motion of conductor. Okay. Now to remember this, I'll be teaching you a simple code. Okay. Here, magnetic field. Okay. Or just take this M. Here, current. Okay. Here, force. So just remember this code. Father, mother, child. Okay. First father, then mother, then child. Father F, force. Mother M, magnetic field. And child C, current. Either you can remember like this, or I'll be teaching you one more code. Here, this is your thumb. Okay. Take this M. Then you have field. Take this F. Then you have current, take this C. So how do you name these fingers? This is your thumb, M, okay, and this is the direction of motion, M, direction of motion or direction of force. Then here this is your forefinger, okay, forefinger, F, forefinger F, field F, okay. Then this is your central finger C, current C, okay. Even using this code, you can remember this. This rule is used to find the direction of motion or direction of force of the current carrying conductor. When you know the direction of magnetic field and the direction of current. Very easy, right? Now you know how to find the magnitude of force, magnitude of Lorentz force, and also to find the direction of motion. Okay. Simple DC motor. Now we are going to study the application of this force. Okay. Simple DC motor. DC means direct current. We know that an electric motor, when you have studied about electric motor, we have heard about electric motors. Electric motors are being used in fan. Okay. Then in case of washing machine, you have motors. Where else? Mixer or mixer grinder. You have a motor. So these electric motors will be helping the device work. Here what is happening? The electrical energy is getting converted into, rotational energy or mechanical energy. Okay, this mechanical energy helps the blades to rotate and the mixer grinder to work. Okay, so mechanical energy it is getting converted to. Now we have to study the principle behind this. Now we have studied Fleming's left hand rule. Okay, we know how to find the magnitude of force. According to Fleming's left hand rule, we can find the direction of force. So here when there is a current carrying conductor kept in a magnetic field, what happens? There is a force created. So this current carrying conductor will start to move, and this motion will be helping us to create the mechanical energy for the devices to work. Okay, so electric motor works because a current carrying wire kept in a magnetic field experiences a force. Only because the conductor is experiencing a force, the motor works. And the working of the motor will help the device work. Clear? We'll be studying about the detailed construction and working of this DC electric motor. Now what are the main parts of a DC electric motor? So this is how it looks like. Here you can see a horseshoe magnet, the north and south pole of the magnet. Then you have a DC battery. So first you will be having the armature coil which is mounted on an axle. This is your armature coil. It is made up of a wire. It is mounted over a soft iron core. You can name it as some A, B, C, D. Okay, this is your armature coil. Next, you will be having split parts S1 and S2 of a ring which is known as split ring commutator. So here we have a split ring. So this ring is split into two parts. We'll be naming it as S1 and S2. Okay, it is connected to the battery and the cell with a wire. Clear? Okay, it is mounted at these positions with carbon roots. The third one is a pair of carbon brushes. Here you have carbon brushes which fixes these split rings here. Clear? Next, a horseshoe electromagnet. You can see the electromagnet. This is your horseshoe electromagnet, north pole and the south pole. Next, you'll be having a DC source or a DC battery. So this is your DC battery. Here, the negative. When the key is given, from here you can see the electrons flowing. Opposite direction, there will be current flow. Okay, when there is current flow and there is an effective magnetic field, you will be seeing that through this current carrying armature coil, what happens? It experiences a force and it will be starting to move. So this is how the construction and the working is. You can see that this armature coil with split rings is connected to the carbon brushes and through which it is given to the battery, the DC battery source. Okay. Now let us understand the working of DC motor. DC motor is a device which is used to convert electrical energy to mechanical energy. So here you can see this is how it looks like. Now you have the magnetic field. This is your north pole and this is south pole. Magnetic field is from north to south direction. Okay. Then you have the armature coil. Its name, here we have the battery. From battery, this part I am marking. This is brush 1, B1 and this is brush 2, B2. Then you have split rings which you can mark as S1 and S2. Okay, I'm naming this coil as A, B, C, D. Okay, now we know that from the battery, when you plug in the key, what happens? Charges starts flowing. Due to the flow of charges, there will be a current. So this is the direction in which current flows from the battery. It is going to B1, from B1 to S1, S1 to A to B, B to C, C to D, D to B2, then from B2 to S2, again back to the negative terminal of battery. This is the direction in which the current is flowing. Okay, now we have the direction of magnetic field. When you take this part of the coil, okay, this part of the coil, you can see that this part of coil is parallel to magnetic field. That is a current flowing direction. The direction of current flow is parallel to the direction of magnetic field. When they are parallel, we have studied that according to Fleming's left hand rule, magnetic field and current should be mutually perpendicular. Only then there will be a force. When they are parallel, there is no force. Okay, so here you don't have to mind. When you take this part, that is AB. When you take this AB part, here you can see that this is the direction in which you have magnetic field. Okay, right to left you have magnetic field. You can see that the current is flowing in the upward direction. This is the direction in which current is flowing. Okay, when you hold your left hand such that magnetic field direction, you're holding your forefinger and upward direction. That is, the central finger is held in the direction of current. Okay, then you can see that your thumb is pointing outward, which means here you can see in the upward direction you will be having your thumb. That is, to this direction there will be a rotation happening to this part of the coil. Okay, now when you take this BC, when you take the part BC, here you can see again magnetic field and the direction of current flow, they are parallel to each other. Okay, since they are parallel to each other, here it doesn't matter. Again, you come to this part CD. This is the direction of current flow. You have magnetic field in this direction. Okay, which means they are perpendicular to each other. When you hold your fingers, here direction of magnetic field, and then you need to hold in the downward direction. That is, here downward direction, you are holding your central finger to get current. You can see that thumb will be pointing inward. So, inward direction means towards down according to this figure. Now, imagine it in a 3D way. So, here you can see in the downward direction, this part of the coil is going to rotate. Okay. So, the rotation is created, force is created. Due to this force, the current carrying coil is rotating. Okay. Now, when it reaches 90 degree, when it rotates and reaches 90 degree, what happens is you can see that the split rings are also rotating. Here you can see split rings in this way. The split rings now becomes in this manner. This is how, due to 90 degree rotation, which means it is losing the touch with the brushes B1 and B2. Okay, connection with B1 and B2 is lost. Here you can see that the current flow will stop in that case. Okay, since the connection is lost, the current is going to stop. The flow of current is going to stop. For that time, that is when the coil is at 90 degree. But still there will be rotation created. Why? Because of the inertia it has gained. The coil has gained an inertia due to which the rotation will be happening. Okay, it will get rotated to 180 degree. 180 degree means now here you're having the coil A, B, C, D. When it takes 180 degree rotation, what happens? It becomes DCBA. Okay, it becomes DCBA. Clear? So, this is DCBA. DCBA after 180 degree rotation. Again, you will be having the current flowing in this case. Now, what happens is the split rings also rotates by 180 degree, which means here you will be having S2 and here S1. Brush will be at the same points, but split ring is undergoing rotation. Here you will be getting S2 and here you will be getting S1, which means the current is going to get reversed in this case. Okay, so due to current flow again and the presence of magnetic field, using left hand rule, you will be getting the direction of force. Okay, that is, in this direction, rotation is going to happen continuously. In the clockwise direction, the armature coil is going to rotate continuously. Okay, due to the electric energy that is provided, we are producing mechanical energy. Okay, after 180 degrees, if it reaches 270 degrees, when it reaches 270 degree, what happens? Again, 270 degree, the split rings. Here, first rotation, S1 and S2 were in this case. Okay, so when it is 270 degree rotation, you will be having S2 here and S1 below. Okay, again the loss of connection, that is B1 and B2, they are not in touch with B1 and B2. Current does not flow, but still due to the inertia, there will be rotation of the coil happening. Okay, after 270 degree, one complete rotation happens at 360 degree. That is, again you will be getting A, B, C, D. The coil will be A, B, C, D. So this is how the DC motor, a simple DC motor works. You need a magnetic field, then you need a current carrying coil, then there will be rotation created due to the presence of magnetic field. The current carrying coil, when it is in the presence of magnetic field, force is created, and this force helps the rotation of the armature coil to produce mechanical energy, and the motor rotates and works. Okay, the speed of rotation of coil, it can be increased by using 4 methods. We have studied that how the coil rotates and how producing a rotation in the coil can convert the mechanical energy to electrical energy. Now these are the 4 ways to increase the speed. First is by increasing the strength of current in the coil. When the current increases, the speed of rotation will also increase. Second, by increasing the number of turns in the coil. If you are using 2 coils, so this is the first coil and this is your second coil. When the number of turns increases, you can increase the rotation also. That is, the rotation speed can also be increased. Okay, one is current, the second is the number of turns in the coil. Third is by increasing the area of coil. When area increases, again the speed is going to increase. Okay, next, by increasing the strength of magnetic field. When magnetic field strength is increased, you can increase the speed of rotation. So we know that there is a magnetic poles. These magnetic poles, then you have a coil, then you have a conductor. All these are factors on which the rotation speed depends on. Functions of split ring commutators. Split rings are also called commutators. Now, what is the purpose of split ring? The split ring reverses the direction of current flowing through the coil after every half rotation of the coil. Just look at this. Here, initially we had A, B, C, D. Okay, so this AB portion is connected to A, B, C, D. AB portion, this A portion is connected to the positive brush B1, split ring S1. Okay, then we have A. Okay, so here the current flow direction, this is the direction of current flow. When you take AB, the current is flowing from A to B. Okay, when you take this part CD, current is flowing from C to D. C to D is the direction in which current is flowing. After half rotation, what happens? This coil will become DCBA. Coil will become DCBA and S1 and S2 will get changed. Okay, here you will be having S2 and here you will be having S1. Now what is happening? We have said that the current is getting reversed. How does the current get reversed? Current is again flowing in the same way, but now we are having DCBA, which means the current is flowing from D to C, C to B, B to A and A to the battery, negative terminal of battery. Okay, you can see this, right? Here, you can see when you take the AB part of the coil, here you have the AB part of the coil. Now the current is flowing from B to A. Okay, when you take the CD part of the coil, this is CD part of the coil. Okay, here the current is flowing from D to C. D to C. What did you understand from this? The current is getting reversed. The direction of current flow is changing. But still, here you have to remember you are not changing the terminals of battery. Without changing the terminals of battery using split rings, because here S1, S2 becomes S2, S1 after a half rotation. Okay. Due to this reason, what is happening? You are able to reverse the current. Or else what will happen? The rotation will be 180 degree, it will go. Okay. After that, it will be returning. If there was no split rings. Okay. Again 180 it will go returning. So, is there any use? No, right? So current direction should be getting reversed. Only then it can continuously rotate in this direction. This form of a continuous rotation is possible. Only then there will be a working of the motor. Okay, this type of rotation cannot make the device work. That is, if it is initially in this way, it will be rotating half. So coming back, after rotation, coming back. There is no use, right? It should rotate continuously in this way. Only then there will be a use. So for that purpose, you are using a split ring. Okay. Coil continues to rotate in the same direction, in same clockwise direction. In this case, same clockwise direction, continuous rotation is happening to the armature coil. Clear? We'll be discussing about electromagnetic induction. Before that, we need to understand what magnetic flux is. So here, just look at this figure. We have seen this at the first part of this chapter. Here you can see a magnet which is moved near a coil and the bulb glows. I have explained you this experiment. Now here what is happening? This magnet. In this magnet, you can see magnetic field lines. So all these are magnetic field lines when you take a bar magnet. Okay, North Pole, South Pole, you will be having field lines. Yes, you will be having field lines. So when this magnetic field line shows the magnetic field around it. Okay, when this magnetic field lines are considered, you can see that when this magnet is moved close to the coil, that is, when it is moved close to the coil, the number of magnetic field lines going or passing through the coil is increasing. Okay, here you can see a field line. Okay, this is another field line. This is another field line. So all these field lines are passing through the coil. So when you move this magnet forward, that is, when the magnet is moved forward, what happens? The number of field lines, that is, these field lines can also pass through the coil. Yes, that is, when you pass this magnet inside the coil, through the coil, what happens? The number of field lines inside the coil or through the coil will increase. So this is called what? Magnetic fluxes. The number of magnetic field lines linked with the conductor is called the magnetic flux, or the number of field lines through a coil is called magnetic flux. Okay. Now if you consider a coil. Okay. If you consider a coil in the magnetic field. So this is a coil. Here you have a coil. So how many field lines are passing through the coil? Just one. Therefore, the magnetic flux will be equal to 1. Okay. Now, if you are considering a coil in this way. Okay. So this is your coil. Here you have a coil. You can see that 1, 2. 2 magnetic field lines are passing through the coil. Okay. Therefore, magnetic flux will be equal to 2. Now, if you are considering a coil here, you can see 1, 2, 3, 4. 4 field lines are passing through the coil, which means the magnetic flux will be equal to 4. So understand what the basic concept of magnetic flux is. It is the number of field lines passing through a conductor or the number of field lines linked with a coil. Clear? Understood what magnetic flux is? From the beginning of this chapter, we have understood that a current carrying conductor can produce a magnetic field. Now, is the reverse possible? That is, if you provide a magnetic field, can it produce a current? For this, an experiment was performed by Michael Faraday, and this is an experiment. He used an insulated copper wire which was wound over a cylinder made up of paper or wood. Okay, then it is connected to a galvanometer. Now, what is a galvanometer? Galvanometer is a device which is used to detect the presence of current. What is the difference between an ammeter and a galvanometer? Galvanometer shows the presence of current, whereas ammeter measures current. How much amperes or milliamperes of current. The measurement, how much quantity of current is measured using an ammeter. Then he had used a bar magnet. Okay, so this is the experimental setup. Now, what is the experiment? Initially, what he does is he used a magnet. Okay, and this magnet was placed closer to a coil. Okay, second, what he does is he is moving the magnet, moving towards and away from the coil. What happens? Then he is bringing it to rest again. Is there any change? So, we'll see what the observations of his experiment are. So, here electromagnetic induction. So, here what is happening? When the magnet is moved to and fro, the number of magnetic field lines passing through the coil is changing. Okay. Due to this change in the number of field lines passing through the coil, magnetic flux will bring a change. Yes, so you can explain electromagnetic induction as whenever there is a change in the number of magnetic field lines linked with a conductor, an electromotive force. This is very important. We'll be explaining it. Electromotive force or EMF is developed between the ends of the conductor, which lasts as long as there is a change in the number of magnetic field lines through the conductor. This phenomenon is called electromagnetic induction. Okay, we'll be explaining what electromotive force is. It is nothing but it is a type of voltage. Here there is no voltage, right? Are we providing a battery? No, right? Without battery, current is produced just using a magnet. Okay, so you will be having a doubt, without battery can we produce current? So here magnetic effects is producing electricity. Clear? So using magnetic effect, if you are producing electricity, it can be called, it is an induction, that is electromagnetic induction. Clear? Now let us explain what are the observations of this experiment performed by Faraday. So first is when magnet is stationary. That is, you can see the setup, you can see the coil. Okay, magnet is held stationary at a position near to this. Okay, in that case there will be no deflection in the galvanometer. No deflection. What does it mean? If there is no deflection, it means that there is no current. So that is, a stationary magnet which is placed near a coil will not produce any current. There is no deflection. Now the second is when the magnet with its north pole facing solenoid is moved towards it. Okay, that is, here you can see the solenoid. This is the north pole of magnet and this is your south pole. Okay, and this magnet is moved towards the solenoid. What happens is, in the galvanometer there is a deflection. Deflection means either it should go towards right or left. So in this case, when the north pole of the magnet is brought near to the coil or the solenoid, this needle of the galvanometer deflects towards right. Okay, so here the deflection is towards right, which means there is a current flowing through the coil. To the solenoid, a current is flowing. So this is your second observation. Third is, as a motion of magnet is stopped, that is, here initially magnet was at this position, it is moved towards the solenoid and reaches a particular point and it is stopped. That is, the magnet is no more moved. In that case, what happens is, there is no change in the number of field lines, right? So here there will be a magnetic field. Okay, there will be a magnetic field. So when you move it towards a coil, what is happening? The number of magnetic field lines passing through the coil will be increasing. Okay, that is, there is a change. Initially, if it was 2, it will become 4. Then it will become 6. There is a change. It can either increase or decrease. There will be a change. Okay, finally, when you bring it to rest, again, when you bring it to rest, that is, magnet is brought to rest, the number of field lines which is passing through the coil will be the same. It is no more going to change. Let's say some 6 field lines are passing through the coil. You're holding the magnet still there. In that case, there is no change brought. Okay, which means there will be no deflection. There is no change in magnetic field lines. Number of magnetic field lines. There will be no change in magnetic flux. There will be no EMF. In that case, there won't be any current. Okay, so no current. Next, if the magnet is moved away from the solenoid, away means it is pulled outward. Okay, you can see it is moving out. In that case, you can see what is happening. The number of field lines is decreasing. The number of field lines through the coil, passing through the coil is decreasing, which means there is a change in the number of magnetic field lines. Again, there will be a current. Now, the difference is, initially here you can see the deflection is towards right, but here the deflection will be in the opposite direction. Okay, it will be in opposite direction. Towards left, deflection will be there. Towards left. Now the fifth one, if the movement is done more rapidly, what happens? That is, you are moving it, you are taking it out, you are moving it in. Moving out, moving in. Rapidly when you are doing it, what happens is the deflection will increase, which means the current will increase. Here the change is happening very fast. Okay, change in magnetic flux is happening very fast. Therefore, the deflection in the galvanometer, let's say initially when you moved it slowly, if it was this much, now the deflection will be more. Okay, you can see the deflection is more. So when it is moved rapidly, deflection will be more. Next, if the magnet is brought towards the solenoid by keeping its south pole towards it. That is just the opposite. Here you can see south pole, north pole. Now, if you are moving in such a way that south-north, this is how you are holding the bar magnet. In that case, the reverse thing will happen. So here when north-south is brought towards the solenoid, what happens? The deflection is towards the right. Now, when south-north, south pole is brought towards the solenoid, in that case, the deflection will be towards left. Okay, this is when it is moving in. Now, when it is, or the magnet is moving out, south-north, it is moving out. What happens? In which direction deflection will be there? Here it is towards left. So, here it should be towards right. Okay, north pole moving out, then it is towards left. South pole moving out, in that case, you can see the deflection is towards right. So, these are the observations that Faraday have got doing the experiment. So, from the experiment, we have understood that the only motion of the magnet can produce an electric current. Or another option is, now we have seen that the solenoid is kept still and the magnet is moved. Okay, if the magnet is kept still and solenoid is moved towards the magnet, even in this case, you can see that the electricity or current is produced. So, we can say that the relative motion between a magnet and a solenoid can produce electric current. Clear? Now, these are the conclusion that he brought from the experiment. First, a current flows in the coil only when there is a relative motion between the coil and the magnet. It is not necessary that the magnet only moves with the coil still. It can be that the magnet is still and the coil is moving, or both magnet and coil. You can bring the magnet and the coil in this way, or it can be taken out. Even in that case, current will be produced. Now, the second point, the direction of current is reversed if the direction of motion or the polarity of the magnet is reversed. That is, either you are moving it in or you are moving magnet out. In that case, what is happening? There is reverse. Initially, north pole moving in that case, deflection was towards the right. North pole moving out, deflection was towards the left. Or the reversing, the direction will change, direction of motion will change. The second case is when the poles of magnet is reversed. North-south is changed to south-north. In these two cases, you can see that the direction of motion or the polarity of magnet, by reversing, you can see that the direction of current is also getting reversed, in which direction the current flow is changing. Third point, the current in the coil is increased by. How can you increase the current in the coil? So, one we have discussed, what is it? The rapid motion, okay? The rapid motion of magnet or coil, that is moving the magnet or the coil very fast. Okay, in and out, if you are moving very fast, in that case, you can increase the current. The use of a strong magnet, you are using a bar magnet. If you are using more stronger bar magnet, in that case also you can increase the current that is produced, increasing the area of cross section of the coil and by increasing the number of turns in the coil. So, here you can see when you increase, if this is your coil, okay, instead of this, if you are using a bigger coil, that is when the area of cross section increases. In that case also, the magnetic flux associated increases, the E.M.F produced or the voltage produced increases and the current increases. Then next is increasing number of turns. Initially, if it was like this, okay, instead you are using a coil with more number of turns. In that case also, you can increase the current, because we know that the current produced, it depends on the area of cross section and the number of turns. Increasing number of turns, the magnetic flux associated will increase and also the current will increase. Faraday's explanation, whenever there is no relative motion between the magnet and coil. If there is no relative motion between the magnet and coil, you can see that the number of magnetic field lines passing through the coil will not change, which means the magnetic flux, no change. Okay, there is no magnetic flux change. If there is no change in magnetic flux, that is either the magnetic flux should increase or decrease, or the number of magnetic field lines passing through the coil must increase or decrease. If there is no increase or decrease in the number of magnetic field lines passing through the coil, there will be no magnetic flux. Okay, no magnetic flux, which means no change in magnetic flux means it implies there is no E.M.F. Okay, there is no voltage. We know that electricity or electric current flows only when there is a battery or a voltage. Now, here it is not the battery. Here we need an E.M.F. No E.M.F. is produced if there is no change in magnetic flux. No E.M.F. means no current. Understood? there will be no deflection in the galvanometer. Second, when there is a relative motion between the coil and magnet, when there is a relative motion, in that case there will be a change in the number of magnetic field lines passing through the coil. If there is a change in number of magnetic field lines passing through the coil, there will be magnetic flux. Okay, you will have a magnetic flux now. If there is a magnetic flux, you will have EMF. Yes, if there is EMF, you will have current. Okay, here there is motion of magnet. Motion means it is mechanical energy, right? Now the mechanical energy is giving us electrical energy. So we can say that in electromagnetic induction, the mechanical energy spent in moving the coil or the magnet to change the magnetic flux is transformed into the electrical energy in the form of current in the coil. Okay, when you are moving, there is mechanical energy. Either you are moving the magnet or you are moving the coil. There is mechanical energy. What is happening to this mechanical energy? It is producing a magnetic flux. It is producing a change in magnetic flux, and this gets transferred into electrical energy, which is seen as the deflection in the galvanometer. You can see the current in the coil. Okay, so this is the electrical energy. Here we have understood that the change in magnetic field lines, the number of magnetic field lines passing through the coil is producing the magnetic flux. And due to this magnetic flux, we have an induced EMF. What does induced mean? Induced means it's forcefully done. Okay. So this induced EMF is producing a current, and this current will be called induced current. Okay, induced current. It is not the normal current, a current that we are producing. Okay, it is induced current. Now we can define electromagnetic induction. Electromagnetic induction is a phenomenon in which an EMF is induced in the coil if there is a change in magnetic flux linked with the coil. When you bring a change in magnetic flux, it is producing an induced EMF, and this induced EMF is producing induced current, which is seen as a deflection in the galvanometer. Okay, so this is how you can define electromagnetic induction. This is a basic definition of electromagnetic induction. Faraday's laws of electromagnetic induction, there are two laws. First one, whenever there is a change in magnetic flux linked with the coil and EMF is induced, the EMF induced lasts so long the magnetic flux linked with the coil changes. Understood? So here we have said that the number of magnetic field lines, when it changes, the magnetic flux is changing. Due to this magnetic flux only, we are having the EMF which is induced. Okay, this induced EMF will last until when? Till there is a magnetic flux. That is till the number of magnetic field lines, there is a change is happening. Okay. If there is no change in the magnetic flux, in that case there will be no EMF. Till when there is a change in magnetic flux, till then there will be an EMF induced in the coil. Okay. Now the second, the magnitude of EMF induced is directly proportional to the rate of change of magnetic flux. Rate of change means with respect to time, what is the change that is brought in magnetic flux linked with the coil. If the magnetic flux changes at a constant rate, a steady EMF is produced. So understood? As we are moving, let's say the rate at which the magnet is moving. If you are moving it fast, which means with small time, the magnet is moving more distance. Okay, the rate of change of magnetic flux will also increase, which means the induced EMF will increase and the current will increase. In that case, you have more deflection. Okay, now if you are moving the magnet slowly, when the magnet is moved slowly, what is happening? In a given time, there is less movement of the magnet. The rate of change of magnetic flux is decreasing, then the EMF will decrease and the current will decrease. If there is a steady flow, okay, at a constant rate, if you are moving the magnet, in that case you will be producing a steady EMF. Okay, there will be a steady EMF that is produced. Okay, factors affecting the magnitude of induced EMF. On what factors does induced EMF depend? First one is on the rate of change of magnetic flux linked with each turn. So here you can see a coil with number of turns. Now what is rate of change? We know that velocity. Velocity is the rate of change of displacement. With respect to time, how much change is happening to displacement? What is the change in displacement? Speed. Speed is the rate of change of distance. Distance by time is speed. Acceleration. Acceleration is the rate of change of velocity. Power. Power is rate of change of work done. All these we know. So here you have magnetic flux. The rate of change of magnetic flux is one factor on which induced EMF depends. That is, the magnetic flux is represented by a Greek letter phi. With respect to time, what is the change in magnetic flux? One factor. And the second factor is on the number of turns in the coil, N. Okay, so if you take the product of number of turns in the coil, then change in magnetic flux of each turn divided by time in which the magnetic flux changes. That is, change in magnetic flux divided by time will give you the rate of change of magnetic flux. Or you can write like this, number of turns into rate of change of magnetic flux. Okay, so this is how you can find numerical value of induced EMF. Clear? Now we know how to find the magnitude of induced EMF. Induced EMF magnitude can be found out by taking the product of number of turns and the rate of change of magnetic flux. To find the direction, we need to know in which direction the magnetic flux is, in which direction the induced EMF is, in which direction the induced current is. To find that, you have two rules. Okay, the direction of induced EMF and hence the direction of induced current depends on whether there is an increase or decrease in the magnetic flux. It can be determined using two rules. First one is Lenz's rule and the second is Fleming's right hand rule. We have discussed Fleming's left hand rule. A similar rule we will be studying here in order to find the direction of induced current. Why did we use Fleming's left hand rule? Fleming's left hand rule was used to find the direction of force, in which direction the conductor is moving. Now here we will be finding the direction of induced EMF using Fleming's right hand rule. Okay, Lenz's rule. Let's see what Lenz's rule is. As we studied, Lenz's rule is a rule which is used to find the direction of induced current. So according to Lenz's rule, the direction of induced EMF or induced current is such that it opposes the cause which produced it. Now just look at this figure. This is Faraday's experiments. Here you can see the magnet. In the first case, the magnet is moved towards the solenoid, towards the coil. Okay, here let's say this is end A and this is end B of the coil. Okay, now here if you are moving this magnet, north pole of the magnet towards the coil, what is happening? There is a deflection being produced. Okay, deflection is towards the right, which means this is how the current flows. This is the direction in which current flows. This is how the current flows, which means the direction of current flow is anti-clockwise. Okay, anti-clockwise. North and south we have studied this way. This is north and this is south. Okay, south or north, which is anti-clockwise. So here you can see north is anti-clockwise. Similar to this, here you have north, which means this end A will be acting as north pole. Now we are moving the magnet towards the coil. Okay, but what is happening here? We have a north pole and this end is acting as north pole, which means there will be a repulsion produced. Okay, there should be a repulsion produced. It is being opposed. Okay, there is opposing. So here the statement you can see is such that it opposes the cause which produces it. Here the producing cause is moving the magnet towards it. But the induced EMF or induced current is in a direction which is opposite to the direction in which it is being produced. Clear? Now the second, magnet is being moved out. North pole is being moved out. Okay, here again we have AB ends. Okay, end A and end B. Now when it is being moved out, what happens? The deflection you can see towards left. This is the direction in which you have current. Current flows in this direction, which means it is clockwise. Okay, it is clockwise. Clockwise means you can see south is similar to clockwise. Okay, south is similar to clockwise. This way it is south, which means this end will act as south. Here we have north. When you are moving the magnet out, here the chances is for attraction, which means it is again opposing. The cause is being opposed. Okay, so the statement gives us a Lenz's rule. Okay, and this Lenz's rule is always based on the law of conservation of energy. Clear? Okay, just remember this. If you are moving the magnet in one direction, the direction in which the induced current is produced will be in opposite direction. That is, cause is being opposed. Fleming's right hand rule. We have studied Fleming's left hand rule. If you stretch the forefinger, middle finger and thumb of your left hand mutually perpendicular to each other, if forefinger shows the direction of magnetic field and central finger shows or middle finger shows the direction of current, then the direction in which thumb is held shows the direction of force or the direction of motion of conductor. Now here you are finding the direction of force. But in this case, in order to find the direction of current or in the direction of induced current, we are using Fleming's right hand rule. Statement is similar. You are stretching the forefinger, thumb and central finger of your right hand mutually perpendicular to each other. If your forefinger shows the direction of magnetic field and the thumb shows the direction of force or motion, then the central finger or the middle finger will show you the direction of current. Not just the current, it is the induced current. So here you can see we have the magnetic field, electric current and force. Okay, you can see all these are held mutually perpendicular. Now, if you are holding your fingers in such a way that this direction, that is forefinger direction, is showing you the magnetic field and the thumb direction is showing you force, then the direction in which the central finger points will give you the direction of electric current. The same rule, that is father, mother, child, or thumb, motion, M, magnetic field F, forefinger, current C, central finger. So, using this code you can remember. So, here you can use Fleming's right hand rule in order to find the direction of induced current. Clear? That's all for today. In today's class, we have discussed about the force on a current carrying conductor, simple DC motor, Fleming's left hand rule. We have discussed electromagnetic induction, how to find the magnitude and direction of induced current. We have discussed Lenz's rule and Fleming's right hand rule. Hope you all enjoy the session. I'll be back in the next session. Until then, stay tuned to LearnoHub. LearnoHub free hai par best hai. Thank you.